Hello. Today we will begin the lecture about Thevenin's equivalent circuit. The theorem can be used for the following issues. First, we can analyze networks with sources that are not connected in series or parallel. Then we can reduce the number of components required to establish the same characteristics at the output terminals. We can make the circuit only an equivalent battery and a resistance. We can investigate the effect of changing a particular component on the behavior of a network without having to analyze the entire network after each change. We can change an element and check the behavior or see the effect of the behavior of the circuit of the network without changing all the circuit, only the needed part. Seven equivalent circuit, we have a two-terminal DC network, can be replaced with the equivalent circuit consisting of an E Thevinen battery and R Thevinen, which is the 7 equivalent resistance connected in series. First of all, we have to remove the portion of the network where the 7 equivalent is to be found, which is the load resistance. We remove the load resistance from the circuit. Then we mark the two terminals of the circuit, which is A and B. First, we remove the resistance or load and mark points A and B. Then we can get we have two parts to analyze. The first one is R7. We calculate R7 by setting all sources to 0. Any voltage source is replaced by short circuit and a current source by an open circuit. Then finding the equivalent resistance between the two market points A and B in the previous step. Then we get E7 by calculating the voltage by returning all the sources back to the circuit to their original position, finding the open circuit voltage between the marked terminals A and B. This step is the most difficult one, and we can see it in the first example. Last but not least, we draw the equivalent circuit, which composes of E Thevinen in series with R Thevinen, and then we return the removed load RL between terminals A and B. Now we can see an example. Find the 7 equivalent circuit for the network shaded. This is a network shaded. The load is RL. First of all, we remove the load and mark the two terminals A and B. Then the example requires to find the current through the load RL for values of RL 2 ohm, 10 ohm, and 100 ohm. First of all, we removed the load resistance between A and B, then mark the two terminals A and B. After that, we have to get our Thevinen. Then we remove the battery and replace it with a short circuit. We put a short circuit instead of the battery, and we need to get the resistance across the terminals A and B as seen from the load point of view. If we connect an ohm meter between terminals A and B, then we will see that R2 and R1 are connected in parallel by passing current from the ohm meter and returning to it. Then R7 equals R1 parallel with R2, which is R1 times R2 divided by the addition. We get R7 equals 2 ohm. The next step, we return the battery back to the circuit, and now we need to obtain the voltage, open circuit voltage across the terminals A and B. The open circuit voltage E7 equals to the battery voltage 9 volt times the resistance where we need to get the voltage across, which is 6 ohm, divided by the addition of the two resistances which are connected in series, 3 ohm and 6 ohm, which is 9 ohm. we get VE7 equals 6 volt. Now we can find the current across the R load for different values of RL, 2 ohm, 10 ohm and 100 ohm. We calculate IL by dividing the terminal voltage or Thevenin voltage by the total resistance, which is the summation of R Thevenin and RL. Then IL equals E Thevenin divided R Thevenin plus RL. We put now RL equals 2 ohm and get the current, which is 0.75 ampere. Then we put the next value, which is 10 ohm, and get the current, which is 0.5 ampere. Then the last value of RL, which is 100 ohm, we get IL equals 6 divided by 102 ohm, which is equal to 0.06 ampere. Now we see another example. Find the Thevenin equivalent circuit for the network in the shaded area of the network. The load resistance, which is R3, first step we remove it R3 and mark the terminals A and B as shown in the figure to the left. Then we have to get the Thevenin resistance or R Thevenin. Then we can turn off the current source by replacing it with an open circuit. We put an open circuit across instead of the current source to suppress its current to 0 ampere. Then we get the resistance as seen by the terminals A and B from the load point of view. Then we get R7 equals the series of R2 and R1, which is equal to R2 plus R1 equals 6 ohm. The next step, we have to get E Thevenin. Then we return the current source again to the circuit, I equals 12 ampere. And now we can get the voltage across terminals A and B, which is the voltage across R1 as the current across R2 equals 0 due to the open circuit. Then V2 equals 0. Then the Thevenin equivalent voltage is equal to the voltage across 4 ohm resistance. Then E Thevenin equals 12 ampere times 4 ohm equals 48 volt. Now we have E Thevenin equals 48 volt, R Thevenin equals 6 ohm. We now return back R3, which is the load resistance across the terminals A and B, equaling 7 ohm. Now we can see another example. Find the Thevenin equivalent circuit for the network in the shaded area. Note in this example that there is no need for the section of the network to be preserved to be at the end of the configuration. All the previous examples, the load was at the right of the circuit or at the end of the circuit. Now the load is located in the circuit in the center to see different shapes of the load and places to place the load in the circuit. First of all, we replace the load and mark the terminals A and B as shown in figure here. Then we have to get our Thevenin. Then we suppress the voltage of the battery to 0. We replace it with a short circuit as shown here. Then we need to get our Thevenin as we suppress the voltage of the source by a short circuit. Then the resistance R3 is shorted or connected across a short circuit. Then the total resistance of the parallel equivalent of R3 and the short circuit equals 0. 0 times 2 divided by 0 plus 2 equals 0. Now we have the remaining two resistors R1 and R2, which are connected in parallel. Then we have R7 equals R2 parallel with R1. We get R7 equals 2.2 ohm, which is 6 times 4 divided 6 plus 4. Now we need to get Thevenin voltage or E Thevenin. We return back the battery, which is 8 volt. And now we need to get the voltage across the terminals A and B, which is E Thevenin. It is the voltage across R1, 6 ohm, which we can get using voltage divider between 6 ohm and 4 ohm resistors by uh, dividing the 8 volt across them. 8 times 6 divided by 6 plus 4. 8 times 6 divided by 6 plus 4, we get E7 equals 4.8 volt. Then we draw the equivalent circuit with E7 in series with R7, and we return back the load R4 across terminals A and B. Another example, find the Thevinen equivalent circuit for the network in the shaded area of the bridge. We have the bridge circuit where the load is across terminals A and B in the center of the bridge. First of all, we replace the load by an open circuit, or we replace the load and mark terminals A and B as shown in figure here. Points A and B are marked, and we remove the load. Then we have to obtain the R7. We turn off the battery by placing a short circuit instead of it. We place here a short circuit. We can connect the short circuit in between point C and C dash. Then we get R1 and R3 are connected in parallel, and R4 and R2 are connected also in parallel, and the equivalent of both are in series. We get 3 in parallel with 6, in series with 4, parallel with 12. 2 plus 3 equals 5 ohm, where 2 is the equivalent of 3 and 6 parallel, and 3 ohm is equivalent to 4 and 12 in parallel. The next step, we need to get E7. We get E7 by obtaining the potentials across R1, which is V1, and the potential across R2, which is V2. Then we apply Kirchhoff voltage law in the above right loop to get E7. V1, we can get it with the voltage divider of 72 volts across R1 and R3. We multiply E times 6 divided by 6 plus 3. We get 48 volt, which is V1. And then we get V2, which is equal to the division of the 72 volt across 12 and 4. We get 72 times 12 divided by 12 plus 4, which is equal to 54 volt. Then we obtain the Kirchhoff voltage law by using Kirchhoff voltage law E7 in the above right loop. Positive E7 minus plus V1 minus V2 equals 0, plus V1 minus V2 equals 0. Then E7 equals V2 minus V1, V2 equals 54, and V1 equals 48. 54 minus 48 equals 6 volt. Now we get E7 equals 6 volt. We now can obtain the Thevenin equivalent by connecting E7, which is 6 volt, with E7 R7 5 ohm, and then we return back the load resistance. We have finished for now. See you in the next lecture. اه ايه اوه يا وعدي. ليه بتسلم على حد؟